Hi, my name is Nikita and welcome to my presentation on moving bed adsorbers for water treatment to remove metaldehyde. Metaldehyde is a pesticide commonly used in crops, and while removal is not easy, it is necessary. Metaldehyde is mildly toxic to humans, and its hydrophilic nature renders universal treatments insufficient. Fixed bed adsorption is inefficient because it operates in batches, leading to lengthy downtime periods and off-site regeneration of carbon. This investigation aimed to simulate the same process in a countercurrent moving bed adsorber with in-situ regeneration, achieved using coupled equations in MATLAB. Phenolic resin carbon was researched extensively as it has an altered surface to make it hydrophobic, perfect for adsorbing metaldehyde. A stationary mass transfer zone could be achieved by allowing the model to reach steady state, as it indicates the process can run continuously. Partial differential equations were derived for the solid and liquid phases, but the only connecting term between the two was Q dot, present in the adsorption terms. Isotherms are commonly used in adsorption kinetics, and here the Langmuir isotherm was used to connect the equations in MATLAB. The PDE-PE function was used as it removed the need to discretize the PDEs by hand, and it had MATLAB solve them directly. The results showed that effective removal could be achieved, but only at low wastewater volumes. Contact time between the water and carbon needed to be maximized to allow mass transfer to happen. Literature has suggested that in-situ regeneration is only economically viable if the carbon rate is at least 12 kilograms per hour, and with this in mind, the maximum water flow rate that achieved enough removal of metaldehyde was 0.11 meters cubed per hour. When making each flow rate equal, the maximum value that could be used was 0.09 before the concentration exceeded limits. This graph shows that the relationship between carbon and water rates is not linear, so purifying more water can require copious amounts of carbon. Experimenting with the simulation showed that purifying 0.5 meters cubed per hour of water requires over 100 kilograms per hour of carbon, which was not efficient. For this reason, the optimum conditions were set as 12 kilograms per hour and 0.11 meters cubed per hour, as it balanced the water purification rates with realistic carbon rates. At the moment, phenolic resin carbon is the best adsorbent due to its surface chemistry, and steam regeneration is the best choice because it preserves the carbon surface. Steady state was achieved, meaning the process could operate continuously, removing the lengthy downtime periods and removing the need for more equipment. In the future, the steam requirements can be calculated to work out the economic case for in-situ regeneration. Studies are looking into newer methods such as UV regeneration and microwave steam reactivation, so these should also be explored further. Multi-component removal to absorb all persistent contaminants using a mixture of adsorbents can also be investigated, as well as further developing this model to make it two-dimensional or even three-dimensional.